So we're going to continue with the cardiopulmonary system by talking about mean arterial pressure, or MAP. And so we've got three main objectives here. So what affects pressure, what's the difference between systolic and diastolic blood pressure, and how does pressure change throughout the systemic circulation. So to start off, remember that flow equals the change in pressure over resistance. So when we're talking about the cardiovascular system, flow is cardiac output, or what volume of blood is leaving the heart every minute. Pressure is just the average pressure in the cardiovascular system, and specifically in the arteries. And the reason we're able to use mean arterial pressure is because arteries hold on to pressure, and at the end of the circuit is the veins. And the pressure in the veins, the vena cava, when blood gets back to the heart, is essentially zero. And so our gradient is the mean arterial pressure minus zero, which will equal mean arterial pressure. And then the last thing is resistance, okay? And so this is something that opposes flow. And in the cardiovascular system, we call that total peripheral resistance. This is affected by radius, specifically of the arterioles, which are the smaller arteries that connect to the capillaries. So when we look at mean arterial pressure, there's a couple ways that we can calculate it. One is we can just take 1/3 systolic plus 2/3 diastolic blood pressure. And we do that because it's a weighted average, because we're in systole for 1/3 of the time, we're in diastole for 2/3 of the time. Another thing that you can do is you can multiply heart rate times stroke volume times resistance. The problem is you can't actually calculate or measure total peripheral resistance. So we can actually estimate it if we know pressure, heart rate, and stroke volume. Okay, and the reason that we're able to do heart rate times stroke volume is because pressure, so if we do this, pressure equals flow times resistance. Well, in the cardiovascular system, flow is cardiac output, and flow equals heart rate times stroke volume. Okay, so mean arterial pressure, average pressure in the arteries. We're not worried about the ventricle, we're worried about the arteries. And so we've got systolic blood pressure, and this is the maximum pressure that's in the arteries, and it's caused by the contraction of the ventricles. And this is directly affected by heart rate and stroke volume. Okay, as blood comes out of the heart, out of the ventricle, well, the heart rate is how often that comes out, and stroke volume is how much that comes out. Then we've got diastolic blood pressure. It's the minimum pressure in the arteries. So, and this has nothing to do with the ventricles, but it's caused by elastic recoil of the arteries. And this question will be on exam 3. What causes diastolic blood pressure? And the answer is elastic recoil of the arteries. Some of you, as you watch this, I know are laughing, but I've said this for years in both 220 and 381 that this question will be on there, and the average is usually between 30 and 40% of the class that gets it right. It's undefeated. Okay, hopefully this semester is a semester that changes. All right, so think about this. Think about it in terms of a balloon. I fill up a balloon, so as I'm blowing into a balloon, that's systolic blood pressure. Well, what happens when I stop blowing into the balloon and if I'm not pinching the end of the balloon off, what happens? Well, that balloon recoils, and that pressure forces the air out. That same thing is happening in the arteries. That recoil pressure is moving blood forward. And so this is affected by total peripheral resistance, okay? So the diameter or the radius of those arteries and arterioles. So with resistance, total peripheral resistance is just how difficult is it to get blood throughout the entire system, the systemic system. When we vasoconstrict, we reduce the radius, which increases resistance. And when we vasodilate, we increase the radius, which decreases resistance, okay? This goes back to the milkshake analogy. If you have a fat straw or a skinny straw and you're trying to consume a milkshake, which one are you going to pick? And most likely you're going to pick that fat straw because it's easier. You don't have to generate as much pressure to enjoy your shake. Now, the other thing I want to show you here is look at how pressure changes. So these first 4 lines here that go up and down, so these 4 right here, that's in the ventricle. Massive pressure swings, okay? So we have as high as 120 millimeters of mercury, but when the heart is relaxing, it's almost down to 0. The arteries also have big pressure changes, but they go 120 to 80. Okay, systolic pressure is 120, diastolic pressure is 80. All right, and then as we go further and further down the system, the arterioles to the capillaries, eventually into the veins, there's really not much change in pressure, but it's really, really low. And as I said it a minute ago, by the time blood gets back to the heart in the large veins, vena cava, pressure is essentially zero. So our gradient is going to be, our mean arterial pressure is going to be something like this, probably a little bit lower, but 100 minus 0. So that's what we use when calculating, or if we're trying to calculate pressure and resistance and flow. And so we're going to end there.